let's continue with the connection constraints with the Kirchhoff's voltage law. So the KVL. KVL is Kirchhoff's the Kirchhoff's voltage law is about how the voltages around each loop or mesh they will behave, right? Or they're constant. So there we can count the voltage rises or voltage drops. That's what this KVL about. But first we need to know what is the voltage rise and what is voltage drop. Based on my past experience, this is probably most confusing points. Is much more confusing than the current entering or current leaving, because that's easy compared to the voltage. Now the voltage, because it's the voltage, the difference between two nodes, right? So other than the current just going through a element, so this is a cross element, a cross variable rather than through variable, and this is the thing. It could be very confusing to some students. So let's see. I just wanted to see what is the voltage drop. Voltage drop. And the voltage drop is let's see, I have node 1 and node 2. I have voltage labeled, and we use the plus minus to indicate the reference mark. So the plus minus, these are just reference marks. This does not see whether the potential at node A is actually really higher than node 2, and node 1 or is really actually higher than node 2. I mean, because in this case we have phasors, right? So these not even the real numbers. But this is reference marks. With these reference marks defined, we can see. We can tell from node 1 to node 2 the voltage drop is V. Okay? And in this case, you can also see the other way from node 2 to node 1, that is the voltage rise. Right? The voltage rise is V. But what's the most confusing part is that the second and the fourth statement, which are also correct. Nothing wrong with this. So from node 1 to node 2, the voltage rise is negative. So this is really confusing. Let's say I have a desk here where I'm sitting at. The desk surface is higher than the floor by maybe 34 inches. And technically I can see the surface of the desk is lower than the floor by negative 36 inches, 34 inches, whatever. Okay, so that's the but in this case we need to be comfortable with all of them correct, right? We need to be comfortable with all of these statements. So this is all correct. Another possible layer of confusion is the actual value of the V, right? The phasor. So the actual value of the actual numerical value of the phasor voltage does not really matter at all for these statements. These statements are going to be correct as long as once we define the reference marks, plus minus reference marks. I hope that will explain this. So what is voltage drop? If from the positive to negative, the voltage drop is whatever labeled variable is. But if you want to see that's from plus to minus, and you want to see the voltage rise, and then you need to put a negative sign in front of what variable is, just like the second statement. And the same thing for the similar thing situation for the voltage drop. if you go the other way around. Okay, so with that, I hope we can explain the KVL. So in this case, the KVL also has three flavors. They are essentially the same, just as like KCL, right? So we can count the voltage rises, and then we add up to so this voltage rises and they sum to 0, and the voltage drops sum to 0, or the sum of voltage drops equal to sum of the voltage rises. But in this case, we need to choose a direction, right? So are you gonna count this voltage rise from so if you from the same direction? Let's see. I have three equations here. So the first equation here is negative V1. So I already labeled the direction here, this clockwise direction. That means I'm counting either the voltage rise or the voltage drop from negative to plus for V1. So we know from negative to plus, the voltage rise is V1. So this is the voltage drop following the direction. So this is a drop, right? And negative V2, and from negative sign to positive sign, because I'm following these, right? So I'm following the direction we labeled. And in this case, negative V2 is another drop, because from negative to positive, that voltage rise is V sub 2, so the voltage drop is negative. And V sub 3, and that's from plus to minus, that's the voltage drop, and V sub 3. And for V sub x, I have the voltage drop. So these are all voltage drops, right? So this is a drop, another drop. So now this apparently is we are doing the adding voltage drops, right? These should add up to 0. I hope this is clear to everybody. Let's look at the second one. The second one here is from plus to minus. I'm still following the orientation or the direction I follow, the clockwise direction I'm following. So this V sub x is the voltage drop, right? And V sub 1 here is, so from minus to plus, the V sub 1, this is the rise, right? And it's from negative to positive, that's another voltage rise. And from positive to negative, and that's the voltage drop is V sub 3. So voltage rise is negative. So this is the rise as well. So now we are adding the voltage, we are kind of using the third flavor, right? So we have voltage drops equal to voltage rises. So this is number 3. And for the last one here is I have V1, that's the rise, right? V2 from negative to positive, that's the rise. And negative V3, that's the voltage rise. And negative V sub x, that's another voltage rise. So this one we're adding the voltage rises. So we are doing the first kind of, we're using the first equation. I mean, if these three are equally correct, right? So there's one slightly preferred over the other two is, let's see if V sub x is unknown, right? If V sub x is unknown, I mean, this one is slightly preferred, right? So 3 is preferred. The reason for that is you can get the answer right away, just as we did for KCL, right? And this doesn't really seem much, but if you're solving the problem, this kind of make your answer, you can get answer much quicker than the others. It will add up. Okay, I think that's about KVL. I'm gonna stop the video and start another clip.